we went through some twists and turns, we looked at this thing, and we wanted to rephrase it as a quadratic so that we could take advantage of the fact that once it's in ax squared plus bx plus c, right, we can look for the discriminant, bless you, and define it to be greater than or equal to 0. Once you do that, those are the conditions for x to be real, and x must be real, right? So you go through this, it does take, I took maybe 4 or 5 lines just to make sure I did this properly, flip around the inequality the correct way. Okay. Once you do that, out pops this quadratic, and this is the solution to that quadratic inequality, okay? You're between a third and 3, okay? Now we are just shy of actually finishing off, like where would I finish? That 1/3 is this value down here, a third, okay? And the 3, as you can see, my scale is not fantastic because I drew this before I knew, well, actually I already knew, but before you knew that it was a third and 3, okay? So really this should go, well, if that's 1, then that'd be 2 and that'd be 3. So this actually goes substantially higher, okay? But just for now, just because I've left it there, that should be 3. So there's my range. There's my range. This is a very hard question, really. So you guys are doing well if you're still grasping what's going on. My last little bit is I really want to know where these are. I want to know where these are. And it's within my reach to find out their locations. So for instance, I would say, what happens when y is a third? What happens when y is a third? And I simply have to solve this. 1/3 equals minus plus 4 on x squared plus 2x plus 4. Just like I did in this line, right? I just want to get this as a quadratic in x, okay? I guess I would cross multiply. I'd have x squared plus 2x plus 4 over here. I would have 3x squared minus 6x plus 12 over there. Let's tidy this up, shall we? If I bring everything over to the right-hand side, this is going to become 2x squared. This is going to become minus 8x, because I'm subtracting 2x. And I subtract 4 from both sides. So this is going to become plus 8. Everything is even. So I'll divide through, which gives me this. And this is not just factorizable. It's perfect. It's a perfect square, right? This is x minus 2 all squared. So therefore I have one and only one solution, namely x is equal to 2, right there. Okay, so there's my point, okay? I will rehearse that process to find the other point, the higher one, by putting in y equals 3 instead of y is a third.
For y equals 3, it's probably less awkward if you put it into what you've already found then. Like if you
as in, I put it into, hold on, where would I have to put it?
The one that you have labeled A, B, and C.
Oh, you mean this one?
Yeah.
Yeah, you absolutely could. Because in some ways, like I've already done that step. Or alternatively, like you can actually see, this is a bit advanced, but you can just machine it out if you like. Because of how similar these two are, and the fact that I'm literally taking the reciprocal, right? What you will find is that you'll get, when you get to this step, you'll be solving this. Everything will be exactly flipped around because this minus 8x will be a plus 8x, and therefore it will become a plus 4x, and therefore when you factorize, it will become x plus 2 all squared. You can go through that. It just takes that many lines, or if you go straight in there, you'll get that solution out. So x equals negative 2 for that guy, and so I've got that point over there. Okay, there is some symmetry to it, and that's owing to the fact that the numerator and the denominator are so very close to each other, okay? But as you can see, it is neither odd nor even symmetry, right? Because it's not happening around the origin, and it's not happening about the y-axis, okay? But it's a beautiful graph, no calculus involved. You just needed to know how quadratics worked, and then we solved this question of domain and range, and that's what answered it for us. Okay, yep.
Where did the 0 equals x plus 2 squared come from?
That one, from doing this same process with 3 instead of a third. I just kind of shortcutted because the process is the same. Leo.
Like for the quadratic formula.
Yes.
You need to discuss if 1 minus 1 equals 0 or not. If it's not 0, so you can't use the formula.
You still can. You still can. I mean, we kind of dealt with this earlier when you weren't here, because we already established that by regions, y can never equal 0 because there are no intercepts, and so that's why we're always above, so that's why we never hit. And so in some senses, because I've kind of already dealt with it, that's why I don't even mention it here. Okay? That was just about the fact that we'd already identified that we'll never hit the axis, right? So y will never equal y can't equal 0, and if you put in y equals 1, right, you get this solution. That's what happens if you solve it. Instead of putting a third or 3, you put in 1. Okay. Now, just one little quick note, right? Do you remember? And this will be much faster now that you already have the pieces there. One of the graphs that I gave you was, from memory, I think it was x squared plus 1x. Yep, that's the one. Okay, and this was relatively simple. It was nice and symmetrical. It looked like this. There. And there. Yep, you happy with that? Do you remember it vaguely? Okay. Now, the beautiful, beautiful thing about this process, okay, is it works exactly the same. Can you see? I can pull exactly the same trick that I did before. Can you see that? Okay. Watch what happens. I remember we said we were just content to say I don't know where those are. They're somewhere. They turn, but who knows where they are? If I answer this question of domain and range, I will find out where they stop. Okay, because I'll be above there and I'll be below there. Right? Let's see if we can pull the pieces together. Let's turn it into a quadratic. Help me out. X squared plus 1 equals yx. Yep. Okay. So let's just put that guy in general form, like so. Okay. From here, that big leap was saying the discriminant has to be greater than or equal to 0 for a real domain, for real values, in order for this thing to be solvable. Okay. So therefore, I say, what is the discriminant in this case? It's going to be b squared minus 4ac. You agree with that? B squared minus 4ac, I want it to be positive. Okay? Y squared minus 4, that is eminently easy to solve. That's y minus 2, y plus 2. Okay? So I want this though to be positive, right? I've got a quadratic and you want the parts that are positive, they're the outside parts, right? So you're going to get y is less than negative 2 or y is greater than 2.
And it just so happens to be 1 and 1.
Bam, right? So do you see how I went from here and said, oh look, I've got y values. Y values, there I am. That's where it exists. That's where I get real values. Inside here, I don't get real values. The function isn't defined, okay? Then of course, all you need to do is supply that back into here and just because it's a beautiful function, okay, you just get 1 and negative 1, okay? So no calculus involved, just understanding the way quadratics work, pulling out this guy, and then seeing, that's great. Isn't that beautiful? You can just find those points with such elegance. So I did it.